and they propagate with the speed of light, disseminating out to infinity from the source in the transverse direction. So these waves are in the in the form of periodic perturbations. So we can detect these gravitational waves with their strange change in amplitude that's given by delta L is the change in length when a gravitational wave passes by, and it changes the distance between two proof masses, and L is the distance when there was no gravitational waves in the fabric of the space-time. So so gravitational waves come in two polarizations that are plus and cross polarizations, and we have constructed ground-based detectors that are the currently ongoing operations are with LIGO and Virgo, and I think there will be LIGO in India as well that will be operational very soon. So there will be mm, a global network of the detectors, and we will be able to detect gravitational waves with more with more precision. So but the space-based detectors are more advanced, and they will be second generation detectors, in likely the LISA detector, and it will have more sensitivity as compared to the ground detector, because ground-based detectors are they have a more kind of seismic noise and other noises. So in the space-based detector there will be no noise, no and it will be like operational by 2034. So in ground-based detectors, we have basically a beam of laser that passes by a beam splitter, and it's disintegrated into two equal beams, and they are then bombarded on the test masses that are reflecting glasses, and then they are also oscillated many times, and then they reconcile on the photo detector, and it basically construct a constructive or destructive pattern, which will let us know that as if any gravitational wave is passing by or not. As if any gravitational wave is passing by, one of the arm length will change by the amount delta L, and whereas the other arm will squeeze by the amount delta L. So in this way we will be able to detect the gravitational wave. All the detectors, we have basically divided the frequency bands into 4 frequency bands that are high frequency band, low frequency band, very low frequency band, and extremely low frequency band. But in my case, as I will be talking about extreme mass ratio in spirals, so this source basically lies in low frequency band, and there's another very fascinating source in this frequency band that are supermassive black hole binaries, and this frequency band is about 0.1 millihertz to 1 millihertz. So we basically parameterize these binaries, and um, there are some physical units that are by convention that have been used to scale the galactic centers. So these binary systems are parameterized by their strengths and mass ratios. So we have a convenient unit that's dimensionless, that is known as gravitational radius, and it's half the Schwarzschild radii, and it basically depends on the gravitational constant, mass of the massive black hole, and the distance to the source. And as we go closer to this to the massive black hole, this parameter increases, whereas this parameter drops as if we come to the Newtonian field limit, and as we go closer and closer to the horizon distance, the this parameter approaches unity, and that's its maximum limit. So in general relativity, we have three methods of analytic approximation that are based on the mass ratio of the binaries and separation between them. Namely, they are post-Newtonian approximation methods, numerical relativity, and gravitational self-force approximation methods. The waveform models we deal with or that are in use for the detection and parameter estimation purposes, those are basically based on post-Newtonian approximation methods, and that is the expansion of these are based on expansions of v by c, where v is the orbital velocity. So these approximation methods are used. They have been extensively used for detection and parameter estimation, and these quantifies the primary in spiral or the early evolution of the in spiral, whereas they don't basically gives us the very last or the ending solutions for these extreme mass ratio in spirals. They only give us an approximation of the early in spiral. Whereas numerical relativity, these methods are basically they deal with in the strong field dynamics, and they are basically used for the comparable mass binaries and time matrix. And we use some iterative numerical methods in order to solve these systems, and they are working well in the for comparable mass binaries and in the regime of immense gravity. But the problem with extreme mass ratio in spirals is that mass ratio is basically the major relativity methods are ineffective for extreme mass ratio in spirals. So we basically require gravitational self-force approximation methods that are currently in like they are currently in construction. So we don't have these available, and I think that yesterday there was another talk on this topic. The person was like working with perturbation theory. So I personally don't know very much about the gravitational self-force approximation methods because they are not in use for the LISA data challenges or sort of things. So so basically, the waveforms I will be talking about, they are basically based on post-Newtonian approximation methods. So the space-based detector, that is LISA, laser interferometer space antenna, that will have competency to detect the gravitational waves in low frequency regime, and it will be operational by 2034. And this basically consists of the constellation of 3 spacecrafts that are arranged at the equilateral triangle, and the middle guiding center of this constellation basically follows the Earth's orbit, and it's lagging by 30 degrees behind the Earth. And it basically consists of the arm length between this constellation is 1 kilometer, but each spacecraft has its own orbit. So like the arm length changes as it orbits around the sun. So this effect is known as time delay interferometry, and this. So I'm not going into the details because I was told that the audience is mixed; they are not very specialized. So I will not go into the details of time delay interferometry. So extreme mass ratio in spirals are very fascinating systems because they are basically present in the galactic centers, and they are not present in all the galaxies, but they are in the galactic centers of Milky Way-like galaxies. So approximately all the galaxies host a massive black hole. if not all, but many galaxies host a massive black hole of these 10 raised to power 4 to 10 raised to power 7 solar masses, and in their galactic centers, and extreme mass ratio systems are formed in the galactic centers. They basically consist of two objects, and the central object is the massive black hole. And the when a compact object comes and hooks in orbit around the massive black hole, it forms an extreme mass ratio system. And this compact object can be a stellar mass black hole, a neutron star, or a white dwarf. So the whole mass ratio becomes very less than one, and the compact object orbits around the massive black hole for about 1 to 2 years, prolonging for I mean 10,000 cycles to 100,000 cycles. So they basically consist of three frequencies: radial, polar, and azimuthal frequencies. And the compact object not only rotates around the massive black hole, it precesses, and it also comes and goes into and out of the plane. So there are different precessional effects that arises during this in spiral, that can be lens thrilling, and like and there can be radiation reaction effects. So not going into the details of everything, but is like a fascinating source, and it is least known as far as now. So there comes the role of stellar dynamics in these systems. Basically, we have three domains that are galactic dynamics, stellar dynamics, like stellar cluster dynamics in the galactic centers, and relativistic dynamics, in which we have relative stars and other compact objects, right? So basically, in the galactic dynamics, we basically deal with the uh, mass densities in these regimes, and dispersion relations we are interested in, and also we take care of the relaxation times. So for the galactic time scale, we have relaxation time of the order of 10 raised to power 15 years, and the dispersion relations are 40 kilometers per second, and like the mass density is about 0.05 solar masses per parsec cube. Whereas if we zoom in this picture in 1,000 times, we come to the cluster dynamics and Newtonian regime. And here the like densities are of the order of 10 raised to power 6 to 10 raised to power 8. That's very dense region as compared to the galactic dynamical scale. And the dispersion velocities also increases, like they are 100 to 1,000 kilometers per second. And the relaxation time is of the order of 10 raised to power 8 to 10 raised to power 10 years. And if we zoom in more, then we come to the relativistic dynamics, and this is the regime where extreme mass ratio in spirals and these systems are formed. And this regime is very important in this case. So basically here we have a massive black hole of the mass like 10 raised to power 6 to 10 raised to power 9 solar masses, and we have like distances that are very close to the massive black hole. So we take them in terms of Schwarzschild radii, or we interpret them in terms of gravitational radius. So in my case, in my studies, I had been like studying them in gravitational units. So we can also interpret them in Schwarzschild radius, because gravitational radius is half time the Schwarzschild radius, so they are comparable, and we can switch the convention. So there are different dynamical processes that are going on in the galactic centers. They are mainly mass aggregation effects, or they can be the Formanels, or the basically what happens in the tidal disruption effects is that as if we have a main sequence star, or even for the white dwarf or neutron stars, there are when these compact object comes closer to the massive black hole, the gravitational pull of the massive black hole tears apart some mass from these compact objects and swallows them. So it results in an instantaneous signal of gravitational wave. As if this gravitational wave signal is not strong enough, then we might have some electromagnetic counterpart for these tidal effects, and they have been seen in electromagnetic studies. So also the second dynamical effect that is very important is for these such like systems of extreme mass ratio in spirals. They are mass aggregation effects. It's such a effect that the gravitational pull of the massive black hole sh- um, uh, like the gravitational pull of massive black hole shows stellar mass objects that are more massive towards themselves, and it ejects the lighter objects to the outer potentials. So what happens is that all the stellar mass black holes comes closer to the massive black hole in the galactic centers, and all the lighter objects like neutron stars, white dwarfs, and main sequence stars, they remain in the outer potential. So in this way, there's a lot of potential for the stellar mass black hole to form an extreme mass ratio in spiral, as they are more massive, and they can hook onto the highly eccentric orbits. So for extreme mass ratio in spirals, there are some conditions that the galactic centers needs to be dynamically relaxed, and the stars for the dynamical relaxation effect, the galaxy must not have undergone any major merger in past 10 raised to power 10 years. So in the case of Milky Way galaxy, it's a very fascinating site to form extreme mass ratio in spirals, because our Milky Way galaxy does not have any major history of the major merger in past years, like almost 10 raised to power 10 or 10 raised to power 11 years. So we are expecting some events in the galactic centers, and there are some other effects that are more complicated, like resonant relaxation effects, in which there are some torques that are applied by the external potential on the star or the massive black hole near the galactic center, that facilitates the formation of extreme mass ratio in spirals. So the extreme mass ratio and spirals are basically complicated systems, and there are many processes that are still we are unaware of, that facilitates these systems. But the overall taxonomy of the orbits are very important. Like the potential must be this spherical potential, like in the terrestrial galaxies, we don't hope to form extreme mass ratio in spiral systems, because in terrestrial galaxies, what happens is that these stars, when they come closer to the massive black hole, they are then ejected onto the highly higher orbits. And they might not come back to the galactic centers. So we are not expecting such systems to be present in the terrestrial galaxies. And also the like the taxonomy of the orbit is quite important here. So in order to compute the event rates, we need uh, the population of the stellar population around the massive black hole for say, for instance, for one galaxy, and then we compute the number of galaxies, like number of massive black holes in our observable range. for LISA detector, as LISA detector can see out to the redshift 20, but it's speculated that Milky Way, the extreme mass ratio systems might be, LISA will be observing them till 4.5 redshift. So basically what we do for calculating the event rates of extreme mass ratio in spirals is that we take the intrinsic rate of stellar eminence around one massive black hole, and there are multiple scaling relations for that, and there are multiple power laws that have been used in the literature. So I was computing these power laws for the most optimistic cases, and we have been following the work of Jonathan Gear and Christopher Berry. So they basically use these laws, and we have different substitutions of alpha, the scaling factor, for different type of the stellar eminent. Like for neutron star, there's different alpha, and for like other populations, the scaling relation varies. And you like we varied the compact object mass from 5.5 solar mass to 10 solar mass. In the case of extreme mass ratio in spiral, we take the 10 solar mass compact object as a standard one, whereas there's no concept of like limiting it to 10 solar masses. We can also vary it from 0.1 solar mass to 100 solar mass, as if we are looking at all the populations. But in my case, we had been looking at only on the stellar remnants that are massive black holes. So we basically range it from 5.5 to 10 solar masses. And then we take the scaling relation in order to estimate the number of galaxies that are present in galactic centers. For that, we have the scaling relation, and then we substitute it in the equation for number of events, and we have this equation. This equation consists of other factors that are the lifetime of the LISA mission that we took at 2 years. It can be 6 months, 1 year, 2 year, 4 years, or 10 years. So there are different regimes of that, and we have to use then the sensitivity accordingly. And the sensitivity was taken from the paper that is the construction and use of LISA sensitivity curves that has recently been published, I think in 2019 it was published by Neil Cornish, and there's one more author, I don't remember. I will post it in the GitHub page. So basically then it also encounters the spin. So there are two types of spins that are for the prograde orbits and retrograde orbits. The retrograde orbits are anti-aligned with the spin of the massive black hole. Like the orbit of the compact object is anti-aligned with the spin of the massive black hole. And in case of prograde orbits, the spin of the massive black hole is aligned with the orbit of the compact object. So basically prograde orbits, the spin of the prograde orbit ranges from 0 to 1, and the spin of the retrograde orbits ranges from 0 to -1. Whereas the spin is such a parameter that is highly uncertain. In the case of massive black hole binaries or compact object binaries, it's really an uncertain parameter. And in case of like studies, electromagnetic studies, it was it's expected to be very uncertain. We cannot estimate it correctly, and whereas the mass we can mass of the massive black hole, we can estimate it very correctly. So we will range the mass of the massive black hole from 10 raised power 4 solar masses to 10 raised power 7 solar masses in order to compute the event rates of extreme mass ratio in spirals in the range of LISA detector. And we took very optimistic cases. There can be more complicated cases in which we add some more effects, like for spin and for eccentricities. There can be more modifications, and we can exclude the massive black holes that consist of cusp instead of core. And there, like, we can include more and more effects into these systems, and the equation of event rates will become more complicated. So as the audience was not very specialized, so I kept the things very like understand. If you have any question or anything is ununderstandable to you, so you can let me know at any time. Okay, let me turn on the battery. Okay. Now, the waveform models of extreme mass ratio in spirals are quite complicated, and the system consists of 17 parameters in general, but these 14 parameters are then reduced to the 40. From 17 parameters, we reduce them to the 17 parameters, whereas we neglect the spin of the compact object in order to reduce the parameters. Because the system is already very complicated, and for detection and parameter estimation purposes, 17 parameters are too much. So basically 17 parameters are includes mass of the massive black hole, then mass of the compact object, then the spin of the massive black hole and angular momentum of the massive black hole is also and then eccentricity of the compact object is an extrinsic parameter, and orbital inclination, and like there are two angles for the location of the source that are elliptic latitude and elliptic longitude, and then there are two more angles for the massive black hole spin, that are polar spin angle of the massive black hole and azimuthal spin angle of the massive black hole, and then we take the distance to the source, and initial direction of the periapsis is also very important, and then azimuthal orbital phase angle, and we also like we call it as mean anomaly in astronomy and astrophysics, and there's also an azimuthal angle of the orbital angular momentum. That's important, and these 14 parameters, three waveform models that have been used and that have been proposed, not extensively used, but have been proposed like one is the analytical clutch waveform model, second is the numerical clutch waveform model, and the third one is augmented analytical clutch waveform model. So the augmented analytical clutch waveform model is basically a hybrid model that combines the early in spiral from analytical clutch waveform model and the later orbits from numerical clutch waveform model. So the all of these models are approximate, and they do not signify the exact orbit, whereas they quantifies an approximation, and among these waveform models, basically we have been using analytical clutch waveform models, and the code for analytical clutch waveform model basically consists of 4 to 5 pages, and it's quite complicated and quite long. So that's why I have not included, but I have given a link for augmented analytical clutch waveform. It is more understandable, but also that is also very complicated, and any specialized person can follow that. So I do not suggest to use these waveform models to the laymen or the people who are not very aware of these systems. So these are very rich systems, and they have very rich physics and dynamics. So basically, we have been using analytical clutch waveform model for the purposes of computational feasibility, because analytical clutch waveform models do not use very much like computational power, but numerical clutch waveform models are more accurate than analytical clutch waveform models, but they use more computational power, a lot more as compared to the analytical clutch waveform model. Basically, analytical clutch waveform model is based on the sum mode approximations of post-Newtonian equations, and they makes use of Bessel functions. So so the basic computational time is taken by Bessel functions, and so that's why these are computationally expensive. So we basically require some waveform model that is not very computationally expensive, and that is at the same time that will be like more accurate as compared to these waveform models. So we are hoping that self-force approximation models will combine with the analytical clutch waveform model and numerical clutch waveform model in order to give the full inspiral of extreme mass ratio systems. So I basically have not included the construction of extreme mass ratio, these waveforms because of the complications, and they are very I think they are not understandable um, for the early graduate, and I don't expect them to be understandable to the master's level. So you can we can basically we can set one more presentation in order to discuss those models, as if you like, any one of you is interested. So we can have one more talk about that, whereas today I'm not going into the details of the waveform models. So basically what I want to discuss is that science implications and science return from extreme mass ratio systems, that is very rich, very influential in the domain of astrophysics, astrodynamics, and fundamental physics, and there will also be some these systems will have some contributions in cosmological domains. So basically what I want to discuss is that the key objective of the LISA mission is to scrutinize the massive black holes, whereas the lower end of the M sigma relations is very uncertain, and we don't know that how these massive black holes were formed and how they were originated and they were born. So we are basically looking from these systems that how the massive black holes were formed, and the how were their mergers and their accretion rates, and basically we are looking for the spin and masses. They are very important parameters we are looking for, because they will let us know about the imprints of the gravitation, like their histories, merger histories, either they were chaotic or they were random. And we will know we will know this information from the spins of the massive black hole, and they will be imprinted on the gravitational waves, basically on amplitude, and and as a consequence we can know about the evolution of the galaxies, how they were formed and evolved in the early times. Or basically we can basically get information about the galactic dynamics, like we don't know about how much of the population is there around the massive black hole, because a lot of information is a lot of population is in the electromagnetic regime, but we expect a lot more population around the massive black hole that is not luminous, and we cannot see it. Basically they can be stellar mass black holes, and so these extreme mass ratio systems will give us information about the mass spectrum of the massive black holes, M sigma relations, and they will inform us about the dynamical processes and where these extreme mass ratio systems were formed, and the dynamical histories of the galactic centers and their coevolution. We also expect such systems to be present in the Milky Way galaxy, and even if the one extreme mass ratio system will be observable in the LISA band from our own Milky Way galaxy, so that will be robust, and it will give us a lot more information in the extreme relativistic regime, and we can also testify the general relativity in those regimes, and we can also get to know about the extreme environments in the galactic centers and their dynamical processes. So basically in fundamental physics we are looking for to testify and the general relativity, near the massive black holes. Basically, we have so far we have information about the compact object binaries, and they do not deal with the extreme gravitational regime. So in the case of extreme mass ratio in spirals, we will have signal from a very strong relativistic regime, and that can let us know about the multipolar moments like mass and spin. And if the extreme mass ratio signal will deviate at the fourth multipolar moment, then gravitation, so we can conclude that gravity is not the ultimate theory of theory, and there can be something else. So these deviations will inform us about some new physics that can be boson stars and Grava stars, that in case of these stars, the signal of extreme mass ratio will not shut off as the compact object will approach the Schwarzschild radii. So it will be continuous, and it will be like emitting when the compact object will cross the event horizon. So these oscillatory modes and the signal amplitude will basically let us know about such systems that may not belong from general relativity, and maybe the central object is not a massive black hole. So these studies can be like dependent on match filtering, the conventional match filtering. But the problem with the conventional match filtering is that the the parameters of extreme mass ratio in spirals are very like they are large, 14 parameters. So for the detection and parameter estimation purposes, we have to go for Markov chain Monte Carlo solutions, and in those cases, it's like we are in a jungle and there are trees and they have different heights. So likewise, there will be different multimodal solutions, and maybe the Markov chains may stuck on some secondary maximas, and they may not inform us about the true value of the parameter. So these systems are highly complicated, and for detection and parameter estimation purposes, we have to go for some new methods and computational methods, and for detection and parameter estimation for LISA data challenges. So we are in LISA data challenges, we are basically trying to de-scope these problems that are basically a hurdle in the detection of such systems. And we are also looking for some cosmographical signatures of these systems, because as if we have a compact object that is a neutron star, and there's some gravitational wave event that is also giving us some electromagnetic signal. And so we can take the galaxy catalogs from electromagnetic observations, and we can correlate it with the gravitational wave signal in order to estimate some like cosmological parameters that can be Hubble parameter. But for that, we must have a certain range of redshift, and in that we must have a catalog of galaxies that may form an extreme mass ratio system, and that's observable in the LISA domain. Like here in this paper that's mentioned over here, what they did is that they took different redshifts and a cubical volume at different redshifts, and they took the galaxies in those redshifts, and they correlated it with the electromagnetic signal, and they correlated expected gravitational wave signal with the electromagnetic signal, and that can inform us about the Hubble constant or Hubble parameter. And we can also like go for cosmological ladders, and we can estimate them. So I think that's fine for now. I just prepared these slides in order to like address an audience that's not very specialized, and that the people who want to continue their studies in extreme mass ratio systems, and they want to participate in LISA data challenges. And these systems basically they are in multi-domains. You can work on stellar dynamics, you can work on data analysis, you can work on the techniques of data analysis, you can go for waveforms or self-force approximation methods. So these systems are very rich in physics, but they are quite complicated, and one have to be specialized, and they have to understand them fully in order to participate in these activities, and continue the studies of gravitational waves from such systems. So
Yes, yeah, if you
I
can continue
basically
on.
expect some questions now.
Yeah, read them for you. So, guys, please do post your questions to the chat or raise your hand. Either of them is fine. So, the first question is from Divyanshu Tiwari. What are the main objectives of LISA before we launch it into the space? Like, what are the major problems that are needed to be solved before we're fully ready for the mission?
Yeah, basically, there are multi-domain problems. First of all, from instrumentation, I don't know very much about instrumentation, but particularly for extreme mass ratio systems, we are having some problems with the data analysis, because these systems consist of a large number of parameters, and it's very difficult to detect the detection and parameter estimation is quite complicated in these cases. So basic problem is with the detection and like parameter estimation technique. We are currently using MCMC, Markov chain Monte Carlo methods, that basically they got stuck on to the secondary solutions, and we have to then run some more complicated methods like parallel tempering. And it's like we give some temperature to the secondary modes and the whole likelihood surface, and it melts the surface, and then and then the global solution does appears. So there are many different challenges, and these are quite complicated systems, and there are a lot of open questions for the data analysis particularly, which we can address. And by the time Lisa will fly, I'm Christopher Messenger from University of Glasgow. He told me that by the time Lisa will fly, we will have a lot of data and a lot of information to interpret at that time. So basically, what we are doing is that we are shifting the detection and parameter estimation methods to the neural network, and that's based on the Bayesian inference, and they are likelihood free approaches, so we don't need to worry about. So I am basically I'm expecting to work for neural networks as well in my PhD, but for that we have for my PhD, I'm hoping to do some work with comparable mass binaries and equal mass binaries. I don't know about extreme mass ratio systems. However, in the domain of extreme mass ratio systems, I'm working for the LISA data challenges that are going on right now. So in those challenges, we have a specific number of signals that are injected into the artificial or simulated LISA data, and then we try to extract it, and we have a limited domain of time for that detection and parameter estimation, and then we have to submit our results to the LISA consortium or whatever the interfaces for the data challenges. So I have just started working with the Ollie, and we are for now we are constructing a toy model, and we have not gone on to the data challenges, because in case of extreme mass ratio, I have told you that this is very complex system, and detection and parameter estimation is such a specialized topic for even for a PhD. So he asked me to just start from the very basic, in which we understand the frequency domain model. And in these systems, we have basically frequency domains, and we cannot plot it in these systems. We basically take, these are very weak systems in the LISA data. So we basically take a power spectral density of these systems, and we then plot it with the analytical LISA curves, in order to see that whether this a particular MRI will be detectable or not in the LISA range.
Yeah. So next we have a question from Bharatwaj. How will be looking for
Mhm.
data handling and analysis of laser detection? Because since it will be in space, so will it be active
Mhm.
all the time or time active?
I do not understand what he mean by all the time active.
Yeah,
He means that all the time we will have some data coming in, right?
Bharatwaj,
Yeah,
I
I mean here on Earth we have LIGO, so it will be operational when we want. Like we want,
Mhm.
we can like stop it when it comes operational. We want like, but in the space, Lisa will be operational like all the time. Like it's revolving all around Earth, and it will be
Mhm.
operational, and it will be collecting data all the time.
Yeah.
So how are we looking to handle that huge amount of data? Like maybe some error can goes on. Like maybe there will be a detection or not, so something like that.
Mhm. So yes, that's the problem, that we will have a large amount of data, and data handling is very popular topic nowadays for Lisa. So I am not very specialized in the overall data handling for Lisa detector. What we do is basically that before the launch of Lisa detector, we have some artificially simulated data, as it has been done for in the case of LIGO, Virgo, and other detectors, that before they started these detectors, before they made them operational, what they did was they basically injected some signals into the artificially generated data, and see that how it works and how it will work. So likewise, we are doing for LISA data. We don't have any real data as far as now, and we inject some signals and we simulate some artificial data, and then we study it. And in the mock LISA data rounds, the first mock LISA data round had been conducted, like it was between 2007 and 2011, and my supervisor participated in that round. And now they are going on. You can basically, if you any of you are in your PhD or master's thesis, so you can approach, you can basically make an ID in, I can show you the site, if you can see LISA data challenges. So what you would do is, you can sign up for this website from your, it's better that you log in from your institutional email address. So they will allot you the whole access they will give you. But as if you are not signing in from your institutional email address, they will give you some partial access, but you will be able to access some data sets over here, and you can play with them, and you can like do some data analysis and submit your results. So as far as now, we don't have any realistic data, and we are like, scientists are working for the to descope the LISA data challenges, and one of that, there's a big data. Yeah. And it will be coming all the time. So basically now the new methods are like neural network methods that are based on the Bayesian inference and other things. But I'm not very specialized in them as far as now, and they are open problems. They are not solved, and they have not been implemented correctly. But they are very robust, and they are computationally not very expensive as compared to the previous data methods and techniques of data analysis. They were very expensive, and they are taking too much computational power. So that's also one of the questions, that we want to reduce the computational power.
Was hope that answered your question. I
I,
also posted the link to the data challenge to the chat as requested. Thank you for pointing it out.
yeah,
Yeah.
that,
So next, Vicky is
yes, you
asking.
can log in and then. Mhm.
Vicky is asked, can you tell me more about Lisa Pathfinder? They said that the results obtained from this precursor machine are better than expected. So what exactly it is?
Yeah, so Lisa Pathfinder is basically one detector that had been sent to the space, and in order to check how it works. Basically, we have in Lisa constellation we have three spacecrafts, and one of them was sent to the space in order to check how it works, and is that it gives a better sensitivity as expected one. So basically, we work with the sensitivity of the detector, and I'm not very specialized in the Lisa Pathfinder. However, the results were very good.
Rafia, we can't hear you. Yeah, we still can't hear you.
Pathfinder, and what we use the sensitivity curves.
Rafia? Yeah, so you were right about to explain Lisa Pathfinder, why the results are better, what results are better, etc.
Okay, I was telling that basically we do not deal with the instrumentation. So we basically deal with the analytic fit or the power spectral density of the detector, or the sensitivity of the detector, and how its sensitivity is more better. I think that the people who are from instrumentation, they can address this question better. But what I know is that we basically use the power spectral density from the instrument from of a particular detector. We can do the same thing for a ground based detectors. So basically what we do is to calculate signal to noise ratio. So we basically take the signal and divide it by power spectral density of the detector, and that gives us the signal to noise ratio of a particular event or a particular gravitational wave signal. So we can talk about that, how good it estimates a signal. And the power spectral density of a detector basically consists of different noise contributions of detector itself. That can be other measurement noise, it can be galactic confusion noise, it can be I don't remember very much, you can look at the paper. The, it's titled at the construction and use of Lisa sensitivity curve. So in order to study the sensitivity of the detector. So these are the sensitivity. These papers tell us about, let us know about the sensitivity of the detector, and I have used this in order to compute the power spectral density. So they basically give us an equation that have some contributions from different noise components of a particular detector. So basically we then divide it from the signal in order to know how loud the signal will be in the range of Lisa. So here is the equation for power spectral density, that basically consists of acceleration noise of the detector. So there are different noises that are arising in the detector. In case of Lisa, there a lot of noise will be from the laser itself, because as much as we make the laser pointed, or monochromatic, there remains some uncertainty and some fluctuation in the laser beam. So there are other different noises that contribute to this analytic fit. And what we do is basically we take this Lisa sensitivity curve, and this curve has been generated from this equation. And we then plot our different signals, and we see that how observable it will be in this range. So this plot basically consists of galactic background that will be in LISA data and massive black hole binary signals at a particular redshift, and MRI binaries, and there are other some neutron star binaries, and this is a very popular like plot in our analysis.
So if I may ask, Rafia, the galactic background is mainly from binary Waveform mergers, right? Hello?
Yeah, can you hear me?
Yeah. So I was asking.
I'm saying that I cannot see the questions now.
Yeah, Rafia, there's a lot of noise and feedback from your side.